Okay, last time we were discussing about the rolling motion of a wheel, not only rolling but also translating. It's translational motion. If a wheel is moving on the surface of Earth, on a parallel surface, it has two kinds of motion. One is rolling, and the other is the translational motion of the center of mass of the wheel. And I said, if the center moves with a velocity of v, then the point during the motion, the point of the wheel that touches the ground has zero velocity or speed. So I hope you have realized this. This is important. And also, the point right at top of the wheel moves with a speed of 2v. Okay? Here you see, in terms of the angular velocity, this point has a speed of 2r times v, w, the angular velocity, and the center is moving omega times r. So, the next is, since we have an object both moving, translating, doing a translational motion, and rotation, we have, when we are trying to calculate the kinetic energy of this object, we have to separate two different kinds of motion, right? One is rotational kinetic energy. This is because of only rotation of the wheel. And the other is the wheel itself moves, okay, with some linear speed. So we have first think about this example, right? We have a mass, a point mass, okay? This point mass is doing a rotational motion around a fixed axis. And the axis, the center of the rotation is this one. And the rotational motion has a radius of r. You see, this point object, mass m, is rotating around a fixed point. So you cannot say that this mass has any kinetic energy, because it's not moving. It's not going at a translational motion. It's only rotating. So we know that because of the rotation, it has angular velocity, because at fixed time, at certain time intervals, it rotates an angle. That's because it has an angular velocity. We may express its kinetic energy, because of the motion, in terms of its angular velocity. And we can start with the usual definition of kinetic energy, 1/2 mv squared. But we have learned that v can be expressed, this linear tangential speed of the object can be expressed in terms of its angular velocity, right? Because v is equal to omega times r. If the rotational motion has a radius of r, and if it has an angular velocity omega, then we may express its linear tangential speed in terms of the angular velocity times the radius of the rotation. So what you see is we have done this. You see, we can express at the end the kinetic energy not in terms of tangential speed, but in terms of the angular speed. So in terms of angular speed, the kinetic energy is 1/2 mr squared, omega squared, and we call this spatial quantity that we multiply the mass by the square of the radius of its rotational motion. Okay, mr squared. This quantity is a spatial quantity in physics, and it is called the moment of inertia, okay, of the rotation. So the moment of inertia of a point mass, if this mass is rotating around a circle, and if the circle has a radius r, the moment of inertia of this mass is its mass times the square of the radius. So you see, at the end, we have expressed the kinetic energy in a similar form in a similar form to the linear speed kinetic energy, 1/2 mv square, 1/2 I omega square. Here I is what I said is mr square, which is the moment of inertia, and omega is the angular speed of the object. So corresponding kinetic energy in the case of rotational motion is 1/2 I omega square. Next, can we express the moment of inertia of extended objects, not the point objects, not the point particles, but what about if you have a disk? The disk is rotating, and you know the mass of the disk is distributed over some surface, a circular area, and you may as well think a sphere, right? A solid sphere. When you rotate a solid sphere around an axis which passes through its center, again, it has mass distributed all over the volume of a sphere. So which mass, which portion of the sphere you have to multiply by r square, which is the radius of the rotation. So these kind of distributed masses, it is somewhat complicated to calculate the moment of inertia, but in this course I will not give you how to calculate the moment of inertia of these distributed masses like cylinder, sphere, disk, whatever. I will only give the results of these calculations. And for example, a cylindrical shell, and you see, if the cylindrical shell is rotating around an axis which passes through its center, then its moment of inertia is its mass times r square, where r is the radius of this shell, because it's cylinder. But if you think a disk, a solid disk, okay, its mass is not only on the rim, but its mass is evenly distributed over the surface of a disk. Okay, in that case, it shows that when you calculate, its moment of inertia is not mr square, but it's 1/2 mr square. Okay, that means if you rotate this disk around an axis which passes through its center, then its rotational kinetic energy will be equal to 1/2 times 1/2 mr square times omega square. Omega is the angular speed of the rotation. Every point of the disk or the rotating object will have the same angular velocity, right? Because wherever the point is to the as the distance to the center of the axis, it will have the same omega. So you don't worry about which piece has what omega have. Every point on the rotating object, every point has the same angular velocity. So only different thing is its moment of inertia, and if you have a hoop, the moment of inertia is mr square. If you have a disk, the moment of inertia is 1/2 mr square. If you rotate a solid sphere, the moment of inertia is 2 divided by 5 mr square. So it's different for different geometries. If your sphere is hollow, that means it's not a solid sphere, its interior is empty, then the moment of inertia 2/3 of mr square. So this, you don't have to memorize this. I will give, if there is any questions about the rotating objects which has extended, I will give at the end of the exam paper or at the beginning the moment of inertia of certain geometrical shapes. So don't worry about memorizing these moment of inertias, but you have to know that the moment of inertia is different for different geometrical shapes. Even when you think that disk, if the disk is not rotating through an axis which passes through its center, but if it's rotating through an axis which passes through the rim, which passes tangent to the rim of the disk. In that case, the moment of inertia, again, will be different. Okay? The moment of inertia both depends on the location of the rotational axis, and also it depends on the geometry of the object. Okay? So in that case, for example, the moment of inertia will not be equal to 1/2 mr square, but 3 divided by 2 mr square. Okay? All right. So, having said this new concept of moment of inertia, let's do an example. Again, you have 2-point masses, and these 2-point masses are connected by a rigid rod that you can ignore the mass of the rod because it's, let's say, it's very lightweight. So you want to rotate this system of 2 masses, 2-point masses, each have a mass m, rotating around an axis which passes through their center of mass, because the center of mass of 2 masses is this point where the middle of the stick or the rod. If you rotate, what is the moment of inertia for this system? But instead, if you rotate the same system through a point where one of the masses is located at that point, the center, what is the moment of inertia in that case? Okay? Do you think that the moment of inertia will be different?
Maybe it's
What? Same? Let's do the calculation then. We have defined the moment of inertia of a rotating object is its mass times the square of the radius that this mass is rotating around. So for the first case, I have to calculate this mr square for each mass separately, right? Because this mass has a radius to the center, r, and it is rotating, let's say, in omega whatever. So what we do is just multiply the mass times the distance to the location of the point where the object is rotating around the center. So it's mr square, and it's the same for the other mass. It's again mr square. You have to, of course, sum. You have to add these two to calculate the total moment of inertia of these two masses. So the result is 2 mr square. In the second case, one object is right at the center. Okay, it is right at the center, so it's not rotating at all. Or you can think that it's rotating with a radius of 0, right? Because it is right at the center. But the other object has a distance of 2r, okay, to the rotational point or axis. So you calculate m times the distance square, which is the square of 2r. In that case, you will have 4 mr square. So in these two cases, the moment of inertia is different. And you may think that, well, you have the same system, you have the same 2 masses, but they are rotating around a different axis, just like these disks, yeah, right? This disk, for example, is rotating around this axis, around this, passing through the center, but in here, it's rotating around a different axis, so it has a different moment of inertia. So also, the moment of inertia depends on which axis the objects are rotating. So, if an object is both translating, like in a wheel, which goes on the surface of the earth without sliding, rotating, and it's moving, it's doing a translational motion. It has 2 kinds of kinetic energy. If you want to calculate the total kinetic energy of a wheel or a disk which moves and rotates when it's moving, you have to add 2 different kinds of kinetic energy. One is the kinetic energy of the translational motion. In that case, you will think that the center of the wheel as a point object. It moves with a velocity of v, speed of v, and you will think as if all the mass is concentrated on the center. So this is the linear kinetic energy. Plus, since the object is rotating, you have to add also the rotational kinetic energy, 1/2 the moment of inertia I times omega square. Okay? But I can express this omega in terms of the linear velocity or tangential speed, tangential velocity, right? Omega is nothing but v divided by r, and if you add these two, you will get 1/2 mv square in parentheses 1 plus the moment of inertia of the wheel divided by the total mass of the wheel times its radius square. Okay? So the total kinetic energy for a rotating object is not just 1/2 mv square, but it is 1/2 mv square 1 plus this quantity. Okay? This will make a difference when you are dealing with objects, okay, rolling on the surface of an inclined plane. Okay? And like before that, let's calculate, let's think of this rolling motion. A disk is rolling, also it's going on this parallel surface with some linear velocity. It is given as 1.41. And it has the radius of 10 centimeters. The problem is, what is the translational kinetic energy of the disk? And you will find also the rotational kinetic energy of the disk when it's going. And at the end, you will find the total kinetic energy. Okay? So, mass is given, the radius of the disk is given, and the speed of the disk is given. The translational kinetic energy is 1/2 mv square and 1.19 joules. Is this the total kinetic energy of the object? No. You also have to calculate the rotational kinetic energy. And since disk has a moment of inertia of 1/2 mr square, if the disk has a radius of r, you calculate this, get 0.595 joules of rotational kinetic energy. And the total kinetic energy of this object, when it's going and also it's rotating without sliding, is sum of these two, 1.79 joules. This is very important when you are calculating the speed of a round object moving on a inclined surface, and you want to find the speed at the bottom. Initially, it is at the top of the incline, which has a distance to the ground h, height, and you release it from the top. Of course, it will start moving, but it will also start rotating, right? It will do this rotational motion, both translational and rotational motion, and when it comes to the end of the incline, what is its linear speed? What is the speed of its center? Can you say that you can find it by just equating the total potential energy in here, which is mgh, to, at the bottom, 1/2 mv square? Can I find doing this? And think then this case, if you say that, okay, I can calculate the speed here, just equating 1/2 mv square to mgh. At the end, v will be equal to, remember, we have done this many times, v will be 2g times h in square root. Okay? Whatever the mass is. Now, if you say so, then I will ask the next question. If there is no any friction on the surface, that means if you release this round object from rest, it will go without rotating. It will slide. Okay, it will slide. It will not rotate because rotation is because of the friction between the surface and the object. So what will be the velocity in that case? The object is going down without rolling, just skidding, sliding. What will be the velocity in that case? Same. Then if the object is going down with the rotation, is it the same speed? No. How can we calculate it? Any idea? And before you calculate or say anything about it, let me ask, will the speed be larger or less if the object is going down with rotation? Who says smaller? Why it will be larger? Okay, we have initially the same total energy, mgh, right? This energy in the, let's say, first case where the object is sliding without rotation, this whole energy, mgh, will go to the translational motion of the object, okay? So the translational motion of the object, that means v, the speed of the center of mass of the object. But in the second case, the same energy, mgh, will be partially the rotation of the object. So some energy will go to the rotation, and the sum of the energy will go the translational kinetic energy. So since the translational kinetic energy deals with the speed, in that case, this speed will be less. Let's see it. Let's do the calculation and see it, okay? So the first thing is, if the object is rotating when it's going down, right? I know how to calculate when the object is not rotating. It's simply square root g times h, 2g times h. But when if it's rotating, when it's going down, this total energy, mgh, will be equal to not only 1/2 mv squared, but the total kinetic energy, which have to include the rotational kinetic energy also, right? I have to add this rotational kinetic energy term, right? But I can express this omega in terms of v, right? Because it's rotating with the same radius. The radius is not changing. Instead of omega, I can put v divided by r. So if you do this and you do all calculations, you see v at the end will not be equal to square root 2gh, but it will be equal to in square root 2gh divided by 1 plus the moment of inertia of this rotating object. It may be a disk, it may be a solid sphere, it may be a hollow cylinder, whatever it is. In all cases, this I will be different. Divided by the total mass of the object times its radius square. So you see, if there is a rotation, then this I will be there. And if we have this term in the denominator, which is larger than 1, the speed will be less, right? If there is no rotation, that means this I is 0, okay, because it's not rotating. This kinetic energy, rotational kinetic energy term is gone, and you recover the same term for the speed, square root 2gh. Okay? Anything which is not clear? Yes.
What about the momentum of inertia?
Moment of inertia.
Yes. Is it in the center or in the edge of the hoop?
Think about this. When it's going down, the object is rotating. What is the rotational axis? Axis is passing through its center, right?
Center?
Yeah. It's rotating around the center. It's not rotating like this. It's rotating like this. So it's rotating around the center, which passes through its center. I understand what your question. It's a good question, but just you can stop the motion and just make the object rotating. So in which axis through which axis the object is rotating, it's around the center.
Maybe if it's jump, maybe there to another.
Well, if it's jumping, it's another story. Okay. So this next question, you have two objects. Okay. One is a hollow cylinder. Okay. The other is a solid, let's say a solid disk. Okay. But they have the same mass. They have the same mass and same radius. In the first case, all the masses is distributed over the rim. But in the second case, since it's a disk, the mass is distributed all over the area. They have the same mass, they have the same radius. When you release these objects from the top of an incline, and the objects are rotating without sliding, when they are going down, which one will have more speed when they end up at the bottom of the incline? Which one will go faster? Which one? Why? Let's use the result of the previous equation, right? The result of the previous equation. So the V for both of them will be 2gh divided by 1 plus I, the moment of inertia, divided by m r square. Okay? Everything is squared. So for disk, or for cylinder, for hollow cylinder, what is I? I. What is I? For cylinder, this one, I is equal to, if the radius is for both of them is r, okay, mr square, right? Well, you can check from this here. It's mr square, okay. So, well, for the disk, if you check, for the disk, it is 1/2 mr square. So let's put these values in here. So for the cylinder, this one then will be equal to, this ratio is 1, right? Because I is equal to mr square. So 1 plus 1, we have 2 in the denominator. So we have 1 divided by square root 2 in square root 2gh for the cylinder when it comes the end of the inclined surface. For disk, again the same, 2gh divided by 1 plus, what is I for the disk? It is 1/2 mr square, right? And we have mr square at the bottom. So 1 plus 1/2 is 3 divided by 2, or if you multiply the 2gh, then you have 2gh. Which one is larger? You calculate 1 over square root 2, square root is around 1.4. 1 divided by 1.4, on the other hand 2 divided by. Anyway, I can easily say that this will be larger. The speed of the disk will be larger. You can calculate it. Because the kinetic energy for the rotational kinetic energy for the cylinder will be large, right? Because mr square. For the other one, it is 1/2 mr square. So more of the energy is gone to cylinder, right? Because it has more kinetic energy, rotational kinetic energy. The other one is less motor rotational kinetic energy. For the one which has less rotational kinetic energy will be cylinder is bigger. 1/√2.
It's 0.8 for the second. For the second 0.8. For the first 0.7.
Okay, this is, you say, 0.8.
8. No, 7. 0.7.
0.7, around 0.7, and this one 0.81. So that's what I say. VD is larger than V cylinder, right? Okay, VD, the disk has a larger speed than the cylinder. As I said, since the cylinder has a rotational kinetic energy 1/2 mr square omega square. On the other hand, the disk has 1/2 mr square omega square, which is less rotational kinetic energy. So the one which has less rotational kinetic energy will have larger linear kinetic energy. It will have larger linear speed. So the ones in that case which has whatever the objects are, the ones which have larger moment of inertia will have smaller speed at the end, okay? Because more of the kinetic energy is gone to the rotation than translation. So this is a general conclusion, but remember, their radius must be the same and their masses also must be the same. But if you are given the numerical values, you don't think about whether their masses are the same or their radius are the same. When you are given the numerical values, just sit down and calculate whatever the result is. Next, 4 objects: solid sphere, hollow cylinder, solid cylinder, that means a disk, and hollow sphere. Each of these objects has the same radius and the same mass, okay? And they are made from different materials, whatever materials are, we don't care. Which object will have the greatest angular speed at the bottom of the ramp? If they are rolling on an inclined surface and they start the motion at the same height, when they come to the bottom, which one has largest angular speed? This time not the linear speed, the angular speed, omega. And to make everything easier for you, I have just written down the moment of inertia for all. So why? Well, the first thing you may do is just this I1, I2, I3, and I4. Just you can sort them from the least one to the largest one. The largest one is I2, right? It is mr square. I2 is the largest. So which one comes next? I3 is larger than I1, and what about I1 and I4? Which one is larger? I4 is larger, right? I4 is larger. I4 is larger than I1. Also, it is larger than I3. What about I1 and I3? Which one is larger? I3 is larger. and I1 is less. The angular speed when they come to the bottom, which one will have the largest, greatest angular speed? Solid sphere. I1. Okay. Who says solid sphere? Who else? The solid sphere has a larger angular speed. What about the hollow cylinder? You say hollow cylinder will have less rotational energy, rotational angular speed? You can say it's the same. The question asks the angular speed, which one has the larger angular speed? The one which has the largest angular speed will have the largest speed also, right? Because it's so. As I said, the one which has less moment of inertia will have largest speed because more of the energy is gone to the rotational motion, translational motion. So I1 will have the largest angular speed. And which one comes next? Omega 3. And next? Omega 4. And omega 2 will have the smallest angular speed because it has the largest moment of inertia. All right. Let's think on this question. We have two solid cylinders. They are rotating about an axis that passes through the center of both ends of the cylinder. Cylinder A has 3 times the mass and twice the radius of the cylinder B, but they have the same rotational kinetic energy. What is the ratio of the angular velocities of these two cylinders? You can express the cylinder A quantities in terms of the cylinder B then. Let's think of the mass of the cylinder A. The cylinder A has 3 times the mass of the cylinder B. So MA is 3 times MB then. And the cylinder A has twice the radius of the cylinder B. RA is 2 times RB. But they have the same rotational kinetic energy. KA, well, not the linear but rotational, so let's put R in here, rotational kinetic energy, is equal to KB rotation. They have the same rotational kinetic energy. What is the ratio of their angular velocities? What are the expressions for rotational kinetic energy? Ka is equal to 1/2 Ia, the moment of inertia of the mass A, times omega A square. Right? This is the expression for the rotational kinetic energy. And for B, 1/2 I B omega B squared. It says they have the same rotational kinetic energies, so I can equate them. IA omega A squared is equal to IB omega B squared. So I can take the ratio omega A squared divided by omega B squared, and this ratio will be equal to IB divided by IA, the moment of inertia of these objects. One is solid cylinder. They are the same. They are both solid cylinders. Okay, their geometry is the same. So let's then express IB and IA. Well, IB for solid cylinder, solid cylinder means disk, right? Disk has a moment of inertia of 1/2 mb r b squared, and the other one is 1/2 m a. But MA is 3 MB, right? MA is 3 MB. I can write 3 times MB instead of MA, 3 times MB. What about RA? RA is 2 times RB. So square it for RB squared. So these and M's will cancel. I will get 1/2, and this will cancel. This will be 2, 1/6, right? And 1/12. So that means it says the ratio, well, this is the square of the ratio, then the ratio will be in square root 1/12. What is the ratio of the angular velocities? Yes. Do we have an answer for that? Kaç? 28. Sometimes these are wrong. Anyway, we can say 0.28. Okay, and the answer is 8. All right. So this will end chapter 10. Not chapter 10. It's not chapter 10. It is chapter 12, right? Or chapter 11. And I will start the concepts of torque and more of it angular momentum. What is angular momentum? Remember, we have making some correspondence between the linear quantities and the angular quantities. We have defined linear speed, angular velocity, angular speed, and linear acceleration, angular acceleration, etc. But we also had the linear momentum, right? In next chapter, we will deal about the angular momentum, and just like the conservation of momentum, you will see that the angular momentum is also a conserved quantity. So we will cover this for next week. Next week is the last week, or we have more?
2 weeks.
We have 2 weeks to go. Okay, for the next 2 weeks, then I will talk about the angular momentum and torque and etc. Okay, so we don't have any labs anymore. All the labs are done. We have done 9 experiments, and we will have 12 chapters until the final. Okay. So I will put also today's lecture on the web page.